Substitution. It's kind of a weird topic because it's called integration by substitution as if it's like its own unique topic that's a standalone that doesn't really kind of fit with anything else, but really it's a foundational topic that fits with everything else. All right, so your integration by substitution, this is the key ingredient to every other type of integration that you're going to learn about. So what that means is if you don't get this down, you don't have a fighting chance of understanding anything that follows. All right, so that's how important this is. If you already know use substitution, then you're ahead of the game. The one thing I will say is just keep an open mind. If you've seen it before, you may have seen it a certain way. I'm going to present it in my way. You may be like, well, I know it this way. Could you do it this way? And I'll tell you in all honesty, I mean, there's a bunch of different ways to do it. Like, I go back to completing the square. There's a bunch of different ways to do that too. I think my way is the best, but every teacher thinks their way is the best. So if you like it, great. If not, go for something else. But I will say there's a reason why I think my approach is the best. Now, it's not mine. It's the approach that I've adopted because I didn't invent any of this. I'm not that smart. I always pride myself on the ability to understand other people's math. I can't say that I'm smart enough to invent it all myself. I invented some, few things. I'll point them out as we go forward. So, use substitution. What are you going to do? I mean, there's a process here. I got this from a textbook. I just copied and pasted it. I don't even know if I read it. I should read it. Nah. Yeah, it's all right. It's pretty much what I'm talking about here, but you'll see. All right, so what you're going to do is you're going to look at the integrand. The integrand is the expression that's contained within the integral. All right, just so we're on the same page vocabulary-wise. All right, you're going to look at the integrand, and what you're going to try to do is identify the part of the integrand whose derivative is a constant multiple of the other part. All right, I'm going to write that down. All right, so try to identify the part of the integrand I'm not so good with the whole English thing. The part of what I said was the part of the integrand whose derivative is that the WHO apostrophe S or WHOSE? Okay. Derivative is a constant multiple of the other part. All right, when I'm talking about parts, I'm talking about factors. So I'm saying the part and the other part. So we're looking at an expression and we're trying to find one expression that when I take its derivative will only be a constant multiple away from being the other one, the other factor. All right, so that's telling me I got to start taking derivatives, but not on paper because I don't want to do that. That's going to take forever. In some cases, in this case, it's not too bad, but in some cases it might take a while. So what I'm going to do is I'm going to isolate factors. In this case, it's pretty clear. I got a factor of 2x, and I got a factor of x squared plus 1. So I'm going to ask myself, if I take the derivative of 2x, will that be a constant multiple of x squared plus 1? No. All right, and the key to being able to figure that out is knowing what a constant multiple is. All right, so a constant multiple is really just differing by a numerical factor. All right, so like for example, 3x is a constant multiple of x, or the 3 is anyway. All right, so it's a constant multiple away from being just the x. So if I said sine x as my parent function, a constant multiple, maybe you have pi. Pi is a constant. Multiply the two together, pi times the sine of x. All right? They have the same parent function, but they only differ by a factor that is a constant multiple. All right? And so that's what we're looking for here. So we know 2x is not an appropriate choice for you. So process of elimination, because we only have two possibilities here, it would have to be the other factor, x squared plus 1. Now, worst case scenario, and I was saying you want to try to do some of this in your head. Worst case scenario, you don't do it in your head. You write it out on paper, and you just use a lot of scrap paper. That's fine. Until you get the hang of it, that's sometimes how it has to be. All right? What you're going to do is take the derivative of u with respect to x. All right? So du dx is going to be equal to what? 2x. All right? So the derivative of what I chose to be u happens to be not even a constant multiple of the other factor. It happens to be exactly equal to the other factor, which is why this is question number 1 in this topic. You know, we got to start off somewhere. All right? But what we're going to do in the next step is bring that dx over to the other side. So we're going to make this du equals 2x dx. All right. The idea is that I want to create it's a substitution technique. I want to replace all my x's with u's. But if I do that, then I have a disagreement with the variable related to the integral, right? The argument. If I change all my x's to u's, then I can't take the antiderivative with respect to x. I have to make a substitution there also. All right. But the good news is we have now a relationship between du and 2x dx, which means the 2x and the dx can both be replaced by a du. All right? So, u du would be my new integral. All right? Because these two guys, the 2x dx, is getting replaced with the du. I just chuck that on at the end. And we defined x squared plus 1 as u. So the x squared plus 1 gets replaced with the u. All right, so we're just doing direct substitution. We're taking pieces out. Now, you may want to reorganize. If it's not something that's comfortable for you, you may want to reorganize your integral and write it this way. X squared plus 1 times 2x dx. All right, multiplication is commutative. You can swap the orders around if you want. If that's the case, then it becomes a lot more obvious that this part is my du and this part here is my u. But the big question with u substitution is always going to be, well, how did I know that that was the u? And in a lot of cases, it was, I didn't. I tried something. It didn't work, so I tried something else. That didn't work, so I tried something else. And eventually you run through all the possibilities and you get something that works. Right? Otherwise, it's not a u substitution question. Right? If you know, like the key, and you'll find this out as we go forward through the unit, you'll find that the key to everything is knowing what kind of problem you're working on. Anybody who has experience with this course, with anti-differentiation, you know I'm telling the truth. Right? It's when you're looking at a problem and you're like, is that u substitution, or is that a trig substitution? Is that integration by part? What am I looking at here? What am I supposed to do? You know, when you're diagnosing the type of situation, you want to work from the beginning of the course to the end. All right, work from the easier approaches to the more difficult approaches. All right, but once you get it down into this form, you can now anti-differentiate just the way you would if this were x dx. So 1/2 u squared plus c. And then because the question was presented in terms of x, our answer needs to be presented in terms of x. So a little reverse substitution. I say reverse substitution, but it's still just substitution. You're just substituting differently, right? But the u is actually x squared plus 1. And so that's my antiderivative. Right? So what we do, and this is completely optional, is we can check by taking the derivative. So apply the chain rule. And you can do it on the fly. It's really not a matter of actually writing the rigorous solution. Power by coefficient, that cancels. X squared plus 1 to the first multiplied by the derivative on the inside is the 2x. That gets you back where you started. So you should be reasonably confident that we didn't just butcher that.
How do you get u squared?
We're just increasing the exponent by 1 and then divide by the new exponent.
You want that simplified?
No.
Simplify
If you simplify it, no, as long as you don't screw it up.
So like if you made it x to the 4th plus 1 over 2 plus c, is that fine?
You'd lose credit because it should, if you're going to simplify, it'd be x to the 4th plus 2x squared plus 1 because you'd have to distribute it out.
Okay.
So let me save you from yourself. Don't simplify. All right. And honestly, I mean, yeah, this one has an answer that's raised to the second power, but more often than not, it's going to be raised to an inconvenient power. I mean, we got a radical over there, so fractional power. This could be to the 7th power. That's a whole can of worms you don't want to open.
So is there anything about this problem that's also substitutionary? You have to, like, just go through the process?
You have to really go through the process. The one thing I always look for when it comes to diagnosing something specifically as u substitution is trying to determine if one part of it, one factor, is the derivative of another part of it. If it's not, then it's probably something else. But that when people say Calc 2 is hard, they say it because of the diagnosis part of it. Where it's like when you're not told what kind of integral it is, how do you know what approach to use? All right? And in a lot of ways, it comes down to experience. Right? But with experience comes knowledge of rules. So those 2 pages that I said, oh, you should know these rules, like little note cards and stuff like that. That's all well and good. You can put formulas down on a note card, but if you don't know enough to look at your note card for a formula, then it doesn't do you much good. So personally, I know that this is u substitution, not just because of that, but because I know, and like this is not me showing off or anything, I've been doing this for 20 years. Like I know all the rules. So I know that this is not an inverse trig rule. I know it's not a trig substitution rule. I know it's not a natural log rule or an exponential rule or any other kind of rule. All right, so now I start looking at other possibilities, and that boils down to techniques. So u substitution, and then all those other fancy things that I named already. All right, so once I go through all, the knowledge that I have related to the rules, once I eliminate all that, then I start getting into process. But you never get into process until you have a good handle on what the rules are. All right. So that's where the idea of a formula sheet or a note card kind of works against you, because when you use it as a crutch, that's when you do yourself the disservice. All right. But for now, we know we're working on a lesson called integration by substitution, so at least we have that. Oh, this is like a doubly looking radical thing, which is of course a typo. So that's for somebody. So what do you think the u is going to be here? That's supposed to be a regular radical, by the way. What's my u going to be? X cubed plus 1. All right. So something to keep in mind. Just thinking in terms of the power rule. If I take the derivative of an expression, the power is always going to decrease by 1, right? So I would never choose the expression that has the smaller power, because it's not going to differentiate up to a higher power. It'll always differentiate down to a lower power. All right, so I wouldn't select the x squared. I would select the x cubed. Now it's a question of, do I want the x cubed or the x cubed plus 1? Now you might say, well, I'll just take the x cubed part. But when you really think about it, the 1 is going to go to 0, so it doesn't make a difference. And if you can wipe out an entire chunk of the integral in one shot, and by wipe out, I mean replace it all with a simple u, that's the best you can hope for. All right, so du is going to be equal to 3x squared. Now I'm going to put the dx over on the right-hand side. It's not really skipping too much in terms of a step. It's just saving you from having to write an unnecessary step. Because if you think back to what we did here, we took the derivative, which created a differential equation. Then we put it in differential form by just swinging the x over to the other side. So it's like, well, couldn't I just do all that in one shot instead of writing 2 lines worth of work? Why don't I just write it in one shot? All right, so instead of du dx equals 2x, I could have just said, all right, it's going to be du equals the derivative of this multiplied by dx, because I'm just going to move it over anyway. All right, so that's what I'm doing here, and that's what you should do. All right, it's a time saver and a space saver and life saver. I don't know, some kind of saver. All right, so now you're at the diagnosis stage. All right, everything's diagnostic in this sense. I'm looking at what I have, and I'm looking at what I need. I know that at this moment, I could swap out the x cubed plus 1 for a u. All right, so actually, let me do that. I'm going to leave the x squared there. I'm going to replace the radicand with a u. All right, because I can do that. That's what I defined it as. So then the question would be, how can I get rid of the other stuff? Well, this is what I have. This is what I need. Because there's an x squared and a dx here, I know I'm on the right track, because the only thing that makes this integrand differ from what I have here in my differential form is a constant multiple. It only differs by a constant multiple, which is perfect. All right, so if that 3 goes away, then I have a direct relationship. I already have a direct relationship, but I have a clean relationship. So what I'm going to do is divide both sides by 3. So this is going to become 1/3 du equals x squared dx. So that's going to allow me to take Is there a high-pitched whine in here, or am I like... Okay. Thought I was having a medical issue. Wouldn't be the first time. So x squared dx can be replaced now with 1/3 du. All right, so this right here is going to go in. You put the 1/3 wherever you want. I'll just put it right in front of the radical.
You can take it outside of that too.
You could also, yeah. Either way. But now I have an integral that's strictly in terms of u. Perfect. That's what I'm looking for. If you have any mixture of x's and u's, it's all over. All right. Assuming that you did all the derivative parts correctly. That's really killing me. Assuming you took the derivative correctly and cleaned things up correctly, if after all that you have both x's and u's inside your integral, then you have a problem. What it means is that one of two things. You either selected an incorrect u, or, more disastrous, it's not a u substitution question. All right? At this point, it would be you selected the wrong u, which is the least of your worries when it comes to the different possible ways in which you could have a calamity. All right, but anyway, I'm going to clean it up. 1/3 u to the 1/2 du. I'm going to increase my exponent by 1, so u to the 3/2, and divide by my new exponent. So when I take 1/3 and divide it by 3/2, that's the same as saying 1/3 times 2/3. So that's 2/9 plus c. And then, well, I've successfully anti-differentiated. Now it's just a matter of bringing back my u. So 2/9 I believe it was x cubed plus 1. And so that would be my antiderivative. Now there's a way to check this on your calculator, but I don't know that we're really there yet, because it's not anything that's going to check it symbolically for you. It'll check it graphically. All right, so we'll cross that bridge a little bit down the road. For now, we're just working on skills. There's some serious rain out there. Oh, that's the page? Oh, crazy. When you were learning about chain rule back in Calc 1, it started getting a little dicey when you incorporated trig. And the same thing happens when you're dealing with U substitution. Because really, U substitution comes from the concept of chain rule in reverse. It's not as cut and dried as that, right? But you have an inner function. They're composite functions. You have an inner function. You're taking the derivative of that inner function, but that's where the similarities kind of end. It's what you do after that kind of distinguishes one approach from the other. But the good thing about U substitution is that really, again, if you know it's U substitution, if you know it's that kind of question, it's just a matter of time. The problem when you're dealing with trig is that there's a bunch of different ways that it could take shape. So what I'm going to do is I'm going to show you a couple of wrong possibilities and how they play out, and then I'll show you the correct one. All right, so here's a wrong one. Let's say I thought my two possibilities were cosine squared and sine. All right, cosine squared x and sine of x. And so I looked at it and I said, you know what? Cosine squared x sounds good. I'm going to go for that one. I'm going to let that be my u. All right. So again, this is an incorrect approach, but I want to show you what happens. And then also how you can kind of develop a little recipe for success. All right. When I take the derivative of this, I'm going to get du is equal to, it's chain rule. The trig functions are kind of weird when it comes to that, because cosine of x, or cosine squared of x, is the same as cosine of x as a quantity squared. So when I take the derivative of this is the same as 2 times cosine x times negative sine of x. Now, if I'm looking at my original integrand, cosine squared x sine of x, but really the whole idea behind U substitution, is for us to take one factor, call it u, and use that factor's derivative to help us cancel out the other factor. So you look at what we have here in my du. I forgot the dx. Not that it's going to end up mattering, but that's overkill. All right, so what would happen here is, I'll just show you real quick. I would have an integral that would have a u instead of the cosine. Now, for the sine, it's like, what do I do? Well, this part of it is good. This is what I needed. I needed a sine of x dx. I have that. But I have all this extra stuff here, the negative 2 cosine x. All right, so what I would have to do here, and this is where it all falls apart, is I would have to divide both sides by negative 2 cosine of x. So I'd be looking at du over negative 2 cosine x is equal to sine x dx. All right, well, what that means is that, yeah, I can replace the sine of x dx, but I'd be replacing it with all of this. Du over negative 2 cosine x. All right, the situation has not improved. In fact, it got a lot worse. All right, now you could actually kind of manipulate your way towards the correct expression from this, but you didn't go about it the right way, right? Because you could actually figure out what u would have to be in order to cancel out the cosine of x, but you've already made this more difficult than it needs to be. So we selected an incorrect u. All right, so that's not the best way to go. All right, but you know, first time through, you look at that and you say, well, how was I supposed to know? Failure, the greatest teacher is. I think that's the right way to say it. So, I'll try the sine of x. Also an incorrect possibility. So, u equals sine of x. So then I get du equals cosine of x dx. This one I'll just talk you through. The u would replace the sine of x, so I'd be left with a cosine squared dx. But I don't have enough here to get rid of cosine squared dx. I only have enough to get rid of a cosine of x dx. Right? I'm still going to have a cosine x left over. Right? So if you were to go through this process using this u, you'd still have an x and a u within your integral. All right? So game over for that one. And so some people actually look at this and say, well, I've tried everything. Well, you didn't, because the one thing you didn't try was letting u equal just the cosine of x. All right? So what we could do is we can think of, and we kind of alluded to this before, the integral as cosine of x squared times the sine of x dx. All right? Sometimes you just want to let your u be equal to the thing that's being raised to a power. I know that doesn't sound very mathy. The thing being raised to the power, the base of an exponential, base of a power function. But sometimes whatever is being raised to a power, let that be your u. Sometimes that's the way to go. All right? Sometimes it's whatever's contained within a trig function or a log function or an exponential function. All right? But you don't know unless you try it. All right? So in this case, du would be equal to negative sine x dx. Well, I don't need to get rid of a negative sine x dx. I need a positive sine x dx. So let me negate my equation. Negative du is equal to the positive sine x dx. All right? Just because it's differential doesn't mean it's not an equation. And you can multiply both sides of an equation by whatever you want, divide by whatever you want, as long as it's not zero. You know, raise it to both sides to whatever power you want. These are all operations that you can do.
Put into a trig sub, please.
Trig sub, no, because trig sub is when you're replacing an algebraic expression with a trigonometric one. But you could do an identity substitution. The thing is that doesn't really... let me just think off the top of my head. 1 minus... Yeah, you get 1, when you simplify, it would be sine x minus sine squared x, sine cubed x. It's, you go right in a circle for that. All right, so at this point, we can do a clean substitution. We can replace the sine of x dx with a negative du. And so my new integral is going to be, instead of cosine squared, it's going to be u squared times, instead of sine x dx, multiplied by negative du, or, clean it up, negative u squared du, integrate that, increase the exponent by 1, divide by the new exponent, negative 1/3 u cubed plus c, with u being equal to cosine of x. I wrote that like really huge, and then I was stuck for space at the end, so I had to write it really tiny. What are you gonna do? What are you gonna do? All right, so 4, 5, and 6 are kind of along the same lines as at least something that we've covered. So those become problems that you could try on your own. But really, I'll just try to get this large enough so you can still see it if you're copying. But really, sometimes it's this that needs to happen in order for you to come up with the appropriate U. And you know, I'll tell you, I've been in the same boat where I've sat there staring at a problem, trying to run through it in my mind, and be like, all right, well that U, no, that didn't work. All right, let me try that U, that didn't work. That U didn't work. Okay, crap, it's not U substitution. Let me try something else. And in my mind, I'm just trying to play through all the different possibilities. Meanwhile, one of the U's that I had ran through in my mind would have worked perfectly well if I did it correctly. Right? Sometimes writing it down on paper is what needs to happen in order for you to actually see what you need to see. Right? And it's annoying because, like, the whole paralysis by analysis thing. You're sitting there, you're taking a test. You don't want to start writing down something unless you have you're going down the right path. You don't want to find out 5-10 minutes into a solution that you went the wrong way. But sometimes you have to go down a path in order to see whether it's the right path or not. Right? So, I mean, when it comes to techniques of integration, that's the biggest piece of advice that I can give you. Is don't be afraid to actually write a solution, whether it's the wrong one or the right one. Doesn't even matter. Just start writing something and see where it takes you. Scrap paper is a good thing.
This is a definite rule. How do you input the cosine squared x? Or you just have to write cosine of x times cosine of x?
No, you do cosine of x, close the parentheses, and then square it. The calculator, it's weird. I don't understand why they do this, but cosine squared x, the way we write it on the TI, whether it's the newer ones or the older ones, it's understood as cosine x squared. That's how you write it if you want to put it in the calculator. It's the weirdest thing. I don't know. Right? Because you kind of want to write it. I mean, I wrote it here as cosine x in parentheses squared, but since cosine builds, the trig functions, they build the parentheses in, you'll find yourself writing it this way every time, and it's kind of annoying. I mean, if you're really paranoid, do it this way. Parentheses for the x, parentheses for the function, and then squared, but this gets the same job done.
Can you just do like cosine x times cosine x?
You could, yeah, if you wanted to, yeah. Sometimes the expressions can get a little out of hand, but you can pick and choose your battles there.